Hello students, Jai Hind. Welcome to my YouTube channel. Today we will be discussing Newton's laws of motion. Actually, in the previous two sessions we have discussed about inertia. Then we have also discussed about the time rate change in the momentum of a body, which gives the measure of the external force that is applied on the body. So we have already discussed the first two laws of motion, isn't it? So in this particular session, we will repeat those two laws as well as we will consider the third law as well, right? And then we will discuss various applications of Newton's laws of motion. And last but not the least, we are going to prove that Newton's second law is the actual law of motion. It is because Newton's first law and Newton's third law both can be derived or rather obtained from Newton's second law, right? So let's start with the first law. Although we have discussed it, let us summarize it. As we are aware, the term inertia, it means resistance offered by a body towards any change in its state of rest or of uniform motion along a straight line. And as you are aware, students, it is the amount of matter contained in the body, which is known as mass, that gives the measure of the inertness of a body. Clear, students? So we have discussed there are three types of inertia: inertia of rest, inertia of motion, as well as we have discussed inertia of direction. So the term inertia was first formulated by Galileo, and that is the reason why Newton's first law of motion, which deals with the concept of inertia, is also known as Galileo's law of inertia. So, what is the statement of first law of motion, students? Every body in this universe tends to remain in its state of rest or of uniform motion along a straight line unless it is acted upon by some external unbalanced force. So what it means is, if a body is at rest, it will keep on lying at rest. If a body is in uniform motion along a straight line, it will keep on moving in uniform motion along a straight line, unless it is compelled to change its state under the influence of some external unbalanced force. So that was the concept of inertia, and this is what first law of motion is all about. And students, you must remember we have discussed various applications based on the concept of inertia, isn't it? We have discussed that while jumping out from a running bus, from a moving bus, a person tends to fall down along the direction of the moving bus. That's due to inertia of motion, isn't it? Then we have discussed beating of carpet by a stick. It can help in removing the dust from the carpet, isn't it? Then when a horse suddenly stops running, then the rider tends to fall in the forward direction, isn't it, students? Then the falling of mango from a mango tree on shaking the branches of the mango tree. These all were the applications of inertia. Then mudguards are provided over the wheels of vehicles. It is because the mud that sticks to the tire, they fly off tangentially. So in order to prevent this, in order that it do not spoil the clothes of the passerbys, so what happens is it is provided with mudguards. So these were all the applications of inertia: inertia of rest, inertia of motion, and inertia of direction. So students, first law of motion, it is based on inertia, right? Every body in this universe, if it is at rest, it will tend to remain at rest. If it is in motion, it will tend to remain in uniform motion along a straight line. So basically, everybody is quite lazy. Everybody is quite reluctant to change its state by itself, right? So basically, all the bodies in this universe tends to offer some resistance, tends to offer some opposition towards any change in its state. So no body in this universe can change its state of rest or of uniform motion by itself. In order to change the state of a body, some external unbalanced force is required. So that was regarding Newton's first law, which we have discussed it in detail in the previous lecture, right? Then comes second law. Second law is based on the concept of momentum. What we have discussed is momentum is given by the product of mass and velocity. We all are aware of it, isn't it? Momentum actually is the net amount of motion contained in the body. Mathematically or quantitatively, momentum of a body is given by the product of mass of the body and its velocity. So what we have discussed was final momentum of a body is mass multiplied by final velocity. Initial momentum of a body is mass multiplied by initial velocity. So what we have considered was a body of mass m, which was initially moving with velocity u. Under the influence of this external force, suppose after time t, the body acquires a final velocity v. This is at t equals to 0 and this is at t equals to t. Right? So in time t, the body has changed its velocity from u to v under the influence of this force, isn't it? So change in momentum. We have discussed change in momentum. Change is always final minus initial. So it will be equal to Pf minus Pi. So m is common, it will give us v minus u. Am I clear, students? So it is the change in the momentum. Final moment of the body minus initial moment of the body. So what about the time rate change? Time rate change in momentum. What it means is the change in the momentum divided by the time during which this change has taken place. So it will be change in momentum divided by the time during which this change has taken place. That is time t. So Newton's second law states that the time rate change in the momentum of a body is directly proportional to the force applied. This is the external force applied. So as per Newton's second law, this external force applied is directly proportional to the time rate change in the momentum of the body. This is the statement actually. So what is the statement of Newton's second law? The time rate change in the momentum of a body is directly proportional to the force applied. And students, remember, the change in the momentum of the body always takes place along the direction of the force applied. Here, no need to indicate the direction because here we are dealing with one-dimensional motion, the body moving along a straight path. Right? So I repeat this statement. Newton's second law is the real law of motion. Later on we will prove that Newton's first law and Newton's third law both are contained in Newton's second law only. So Newton's second law, that's the ultimate law of motion actually. That's the real law of motion. Second law states that the time rate change in the momentum of a body is directly proportional to the external force applied on the body, and the change in the momentum of the body takes place along the direction of the force applied. So that's the perfect statement of Newton's second law, isn't it? Now, v by minus u divided by t, that will give us acceleration. So F is proportional to ma. A is acceleration. And students, as we have discussed earlier, in order to eliminate this proportionality sign, we need to introduce some constant. Let that constant be k. Now in SI or in any other suitable units, the value of k is determined to be 1. When the mass is measured in kg, acceleration in meter per second square, F in Newton, then the value of k is found to be 1. Therefore, F is equal to ma. So this is the consequence of Newton's second law of motion. Second law of motion is stated in terms of time rate change in the momentum of the body. Right? And F equals to ma, this is the consequence of Newton's second law of motion. So basically Newton's second law of motion basically gives us a method to measure the force acting on the body. Clear? So this is force is equal to mass multiplied by the acceleration produced on the body. This expression gives a method to measure the external force applied on the body. This is the consequence of Newton's second law of motion, right? So after discussing the statement of second law, we can deeply try to understand the consequences of Newton's second law. The consequences of Newton's second law. First and foremost, consequences. The mass of the body measured by this formula. It is known as the inertial mass. This mass is known as the inertial mass. Why it is known as inertial mass? We'll discuss it. Now look students, again in the previous lecture we have discussed, if a force is applied on a lighter body and consider the same force to be applied on a heavier body, in which case greater acceleration will be produced, obviously in the case of lighter body, because acceleration for constant force, if F is constant, then acceleration is inversely proportional to mass. So for heavier body, the acceleration produced is small. For lighter body, the acceleration produced will be much larger for the constant force. Isn't it? So what I mean to say is that lighter bodies which contain small amount of matter inside it, they offer lesser resistance towards any change in its state of rest or of uniform motion. While the heavier body which contains large amount of matter inside it, it offers much more resistance, much more opposition towards any change in its state of rest or of uniform motion. So, heavier body possesses more inertia, more inertness as compared to the lighter bodies. Right? And we have discussed mass is the physical quality which measures the inertness of a body. So that is the reason why the mass of a body measured by this formula is known as the inertial mass of the body, because this mass of the body tells us regarding the inertness of that particular body, right? So this is the inertial mass. So this is one of the consequences of Newton's second law, which can be used to determine the inertial mass of a body, right? Second consequence is, students, by using this formula F equals to ma, if we are able to calculate the acceleration produced in the body and mass of the body is known to us, then by using this formula we can easily calculate the force which is applied on that particular body. So Newton's second law can be used also to determine the force that is being acted on a body by knowing the mass of the body and by noting down the change in the velocity per unit time, which is the acceleration. So if acceleration is known, mass is known, then the force which is acting on the body, it can also be easily determined. Right, students? So these are the consequences of Newton's second law of motion. Now before we proceed, we need to discuss some applications of Newton's second law as well. Just now we have discussed Newton's second law can be stated only and only in terms of the time rate change in the momentum of the body. That is, the force which is the external force acting, it is, if you write the constant of proportionality as 1, it is time rate change in the momentum of the body. Time rate change in the momentum of the body. Time rate change in the momentum of the body, right? And time rate change in the momentum of the body is m v minus u. This is the change in the momentum divided by time, right? So this is the expression. Now using this mathematical expression, there are various applications of Newton's second law. I'll give some very, very interesting applications. For example, this is a building and this is the roof, and same building, so it will be of the same height and this is a pucka floor. Pucka floor means it is cemented one. This floor is cemented. And this is kacha floor. Suppose mud is over here or sand is over here. This is kacha floor. This is kacha floor. Suppose heap of sand is placed on the floor, right? So it will act as a kacha floor. A person accidentally falls from here, from the height. Now, in this case and in this case, in both the cases, he will fall through the same distance, in which case the person will get more hurt. Obviously, in the case of pucka floor. Why is it so? It can be easily explained using this concept, right? Now look, as the person falls, then on hitting the floor, on hitting the ground, the velocity of the person will abruptly become zero. So the velocity will abruptly become zero from some finite value, isn't it? So in this case, the change in momentum is taking place in very, very less time. This change in momentum is taking place in very, very less time. Right? The change in momentum of the body when the person falls on a pucka floor takes place in very small time. So, if this time is very small, then the magnitude of this force will increase. So, the impact of force on the person falling on the pucka floor will be more devastating. Is it clear? The magnitude of force or the impact of force on the person will be much, much greater. While on the other hand, if the same person falls through the same height on a kacha floor, which is having heap of sand, in this case also, the person falling on the kacha floor will eventually come to rest. Its final velocity will eventually become zero. But in this case, the same change in the momentum will take place in much longer time. It will take place in much longer time. So if t increases for the same change in momentum, the impact of force will decrease. And in this case, the probability of the person getting hurt will get sufficiently reduced. Is it clear, students? Let's consider another application, right? You all must be fond of playing cricket or watching cricket. Now, what is the technique of catching a ball? Now, when a fielder tries to catch a ball, the proper technique is to take the ball like this and to pull his hand in the backward direction, or to catch it like this, not to jump over the ball, isn't it? The player needs to give some time and the player needs to pull his hand in the backward direction like this. This is the proper technique of catching a cricket ball. By doing this, a player saves himself from getting hurt. Why is it so? Because by lowering the arms while taking a catch, a player increases the time during which the catch is completed. I repeat, by lowering the hands while taking a catch, a player increases the time during which the catch is completed. So, the change in momentum of the body. Obviously, there will be a change in momentum of the body due to the change in its velocity. The ball will be in the hand of the player and eventually it will come to rest. So, obviously, there is change in velocity or there is change in momentum. So, if the time during which the catch is completed increases, it means that the change in momentum of the cricket ball takes place in much longer time. And if t increases, then the impact of force will get decreased. So, in that case, the ball on impacting with the palm of the hands of the player, it won't hurt. Is that clear, students? So, while taking a catch, a player always tends to lower down his hand so that the catch is completed in much more time, so that the change in the momentum takes place in more time. So as a result of which, the impact of force get greatly reduced. So these are some of the applications of Newton's second law of motion. and it can be understood in terms of the time rate change in the momentum of a body. The time rate change in the momentum of the body, that actually gives the measure of the force that is being acted on the body. Clear, students? So now, after discussing these applications, we need to discuss third law as well, right? So we have discussed first law, it's based on inertia. Second law, it's based on the time rate change in the momentum of a body. Now third law, very interesting one. Third law simply states that to every action, there exists an equal and opposite reaction. This is the statement. To each and every action, there always exists an equal and opposite reaction. In simple words, forces exist in equal and opposite pairs. I repeat, forces exist in equal and opposite pairs, which means that if the two bodies are interacting with each other, they may be interacting electrically, they may be interacting with each other magnetically, right? So, or they may be interacting with each other due to some gravitational force. So, whenever the two bodies interact with each other, then the force exerted by this body on the other body would be exactly equal and opposite to the force exerted by the other body on the first body. So, that's action-reaction concept. To each and every action, there always exists an equal and opposite reaction, and that is possible only when the forces exist in pairs. So let me elaborate this statement. Let's consider a simple example. This is a tabletop. This is a tabletop. Suppose consider it to be body B, and a body is placed over here. This is a body. This is a body placed over here. This is body B. Is it clear, students? Now, obviously, this body A, due to its weight, will exert a force on the table. It will exert a force on the table in the downward direction. That can be considered to be action. That can be considered to be action. It is actually the weight of body A. Weight of a body always acts in the downward direction. That is along the radius of the earth towards its center, right? So anyway, this is the weight. So W is the force, which is the weight of body A exerted on body B. As per Newton's third law, same force is exerted by body B on body A. This is reaction. It may be denoted by R. So this can be termed as action and this can be termed as reaction. And remember, there is no hard and fast rule that this is to be mentioned as action and this is to be mentioned as reaction. It can be interchanged, right? So, force exerted by body A on body B, if that is considered to be action, then the force exerted by body B on body A, that is considered to be reaction. And always remember, R is equal to minus W in the vector form. So, what does this equal sign represent? That reaction and action both are equal in magnitude. What does this negative sign represent? This negative sign represents that they are always oppositely directed. The angle between these two is 180 degrees. They are oppositely directed. Right, students? So, it is the case of action-reaction. Similarly, this is the first illustration. Second one. Suppose these are the two bodies. This is body A and this is body B. They are not in physical contact. They are at a separation from one another. This is the line joining their centers. So, if this body exerts a force on this body and it is given by FAB, then equal and opposite force will be exerted by body B on body A. Here again, if this is known as action, this may be termed as reaction. So here FAB would be equal to minus FBA. what it suggests is the force experienced by body A on body B is equal and opposite to the force exerted by body B on body A. If one is called action, the other one may be termed as reaction. Clear, students? So what's the main conclusion basically? Now, first point, action-reaction acts on a body and it is immaterial whether the body is at rest or in motion. Remember, action and reaction, they can act, these are the forces which can act on a body whether the body is at rest or the body is in motion. It doesn't matter. Second point, so body can be at rest, body can be at rest or in motion. Second, for action-reaction forces, the two bodies under consideration, they can be physically in contact with each other or they may be separated by some distance. So it is immaterial whether the bodies are in contact or they are at a finite separation from each other. In both the cases, action-reaction force can act, right? So there can be physical contact between the two bodies under consideration or they can be separated by a finite distance. Separated by a finite distance, right? Third, which is very, very important, action-reaction, students, they act on two different bodies. Look, this is action and this is reaction. This can be termed as action, this can be termed as reaction. So, they act on, action and reaction act on two different bodies. And students, this is the only reason because of which, although they are equal in magnitude, oppositely directed, but they do not cancel out the effect of each other. They never cancel out the effect of each other. Forces can get cancelled out only if they act at the same point and are equal in magnitude and opposite directed. For example, suppose this is a body and here 5 Newton is acting and in the opposite direction this 5 Newton is acting. Now here both the forces are acting at the same point. Both are of equal magnitude and opposite directed. So here they will cancel out the effect of each other. Net force will be equal to 0. But here these two forces are equal in magnitude. They are opposite directed. But they are acting on two different bodies. They are not acting at the same point. They are acting on two different bodies. They are acting on two different bodies. So although action and reaction are equal in magnitude, opposite directed, but still, mark my words, but still they do not cancel out the effect of each other because they act on two different bodies. So students, over here, the body A is at rest not because the action and reaction are getting cancelled out. They can never get cancelled out. Action and reaction can never get cancelled out. The body over here, body A, is at rest because the weight of the body, which will act at point A, it is getting balanced by the reaction force exerted by body B on body A. So please do remember this very, very vital and important point. Action and reaction, although they are equal and opposite, they never tend to cancel out the effect of each other. They can't cancel out. They can never cancel out. It is because action and reaction always acts on two different bodies. As I have explained here, the body A is at rest, not because action and reaction are getting cancelled out. It is because the weight of body A, which acts at this point, it is getting balanced or getting nullified by the reaction force, which is exerted by body B on body A. Clear, students? It's a very, very important concept. So, third law states that to each and every action, there always exists an equal and opposite reaction. So, that's the statement of third law. Okay, now let's discuss some applications of third law of motion. First application is we are able to walk on ground. That's because of action-reaction concept. Now students, look, when we walk on the ground, our foot gets slanted and it tends to push the ground in the backward direction. That is action, right? And an equal and opposite force is exerted by the ground on the person walking. So it's horizontal component, the horizontal component of the reaction force that makes the person to move in the forward direction. Now have you imagined why it becomes extremely difficult for us to move on a ice cube, on a large block of ice? It is because while walking on a large block of ice, we won't be able to exert a sufficient large force in the backward direction, so that the reaction force also becomes too small, as a result of which we tend to skid and we are unable to walk on huge block of ice, isn't it? Second application, while firing a bullet from a gun, what happens is the gun recoils. It gives a jerk in the backward direction. And that is the reason why we need to hold the gun very tightly. It is because when the bullet is fired, so that's action, right? It exerts an equal force to the rifle in the backward direction. And that is why recoiling of the gun or the rifle takes place. Similarly, during the propulsion of rocket, what happens is, students, the fuel gets burnt, it gets consumed, and the exhaust gases tend to come out through the nozzle with very, very high speed. So that is action. And an equal and opposite force is given to the rocket in the upward direction. So that's the reason why the rocket is able to propel in the forward direction. Similarly, there are some other applications as well. Like when a person jumps from his boat, when he reaches the shore, then he jumps from his boat. Then the boat tends to move in the away direction, away from the shore. That's again due to action-reaction concept. While swimming, what happens is a person with his arms tends to push the water in the backward direction. That can be considered to be action. While on the other hand, the water exerts an equal and opposite force on the swimmer in the forward direction, which enables the swimmer to move in the forward direction. Isn't it, students? In the case of birds, if a bird tends to raise the height or it tends to go upwards, then what happens is the bird tends to flap its wings, both the wings. So by doing it, what happens is it exerts a force on the air in the downward direction. That's action. That may be considered to be action. And as per Newton's third law, the air exerts an equal and opposite upward force on the bird, which enables the bird to gain height or altitude. Clear? Let me tell you one more interesting example. Suppose an astronaut or a cosmonaut is in open space and he wants to return to his spaceship. Then what he intends or what he needs to do is that he needs to throw something in a direction opposite to which the spaceship is moving. In doing so, what happens is if he throws anything like in that direction, he will himself experience a force in the opposite direction, so that he will be able to move towards his ship and he will be eventually able to return to his spaceship. So that is again due to the action-reaction concept. So there are various applications of Newton's laws of motion. Now since we have discussed all the three laws, we need to consider the last topic, which is the Newton's second law. It is actually the real law of motion. Why is it called so? Newton's second law is known as the real law of motion because Newton's first law and Newton's third law both are contained in Newton's second law. Let me clarify this point. Now we know that force is equal to mass into acceleration. This is the consequence of Newton's second law. If no force acts on the body, that is, in the absence of any external force, F is 0, therefore Ma would be equal to 0. Now since mass of a body can't be equal to 0, which means that product of mass and acceleration is 0, which means that acceleration would be 0. This is a fundamental fact, students. In the absence of any force, the acceleration is 0. Acceleration will be only produced under the influence of some external unbalanced force. So in this case, if the external force is considered to be absent, acceleration produced in the body would be 0. Now, from first equation of motion, what we obtain is V is equal to U plus kT. U is the initial velocity, V is the final velocity, T is the time, A is the acceleration. Therefore, V is equal to U plus 0 into T. In the absence of any external force. So if no net external force acts on a body, then acceleration is 0. In such a case, V would be equal to U, it would be equal to constant. What it means is that no force is acting on a body and the body is lying at rest, that is, its initial velocity is 0, then its final velocity will also be 0. That is, in the absence of any external force, the body, if it is lying at rest, it will keep lying at rest only. That is what Newton's first law is all about, isn't it, students? And in case the body is moving uniformly along a straight line with speed of, say, 5 meters per second, then its final velocity after some time will also be 5 meters per second because V is equal to U. Therefore, if no net force acts on a body, the body will keep moving along the same straight line with the same speed. So that is inertia of motion, which is actually the Newton's first law of motion. So this is the mathematical verification of the fact that Newton's first law is contained in Newton's second law. Similarly, Newton's third law is also contained in Newton's second law, and that is the reason why Newton's second law is known as the real law of motion. So students, I hope you have enjoyed this session and you have benefited from this session. Now the laws of motion must be crystal clear to you. Newton's first law, law of inertia, right? Newton's second law deals with the time rate change in the momentum of the body. Newton's third law, action-reaction pair. To each and every action there exists an equal or opposite reaction. And we have discussed numerous applications. So do remember 2, 2, 3, 3 applications of each of these 3 laws, right? So students, I hope you will study very well and do take very good care of yourself and keep doing the good work, right? Thank you.